the seminar. I want to thank members of the national labs and the Department of Energy for providing materials to me today. I don't think there's a single person on earth who is an expert in all of the aspects of fiber optic sensing, especially some of the newer ones such as chemical sensing and quantum sensing. So I'm going to follow materials that have been given to me. These are all in the public domain. This is being recorded, and you'll have a chance to peruse this. If you ask me questions at the end and they're very, very detailed and beyond my expertise in certain areas, then we will find out those answers or put you in contact with experts and get you those answers afterwards. The next slide is a summary that I put together describing basically the types of measurements that we're making. The fiber is acting as a sensor. We are making measurements along the length of the fiber. It's distributed sensing. We use a light source, propagate light, transmit it through the fiber. Some of the light is backscattered. It's non-specular reflection or scattering back from heterogeneities in the fiber. If there are temperature or strain or acoustic or other properties in the materials in the variables along the fiber, then that changes the characteristics of the backscattered light, and that's basically how we're making direct measurements of temperature, acoustic, velocities, and so on. There are 17 national labs in the United States. The ones that are primarily working on advanced sensing, including fiber optic sensing, are shown in red. Some of them have multiple locations. There's National Energy Technology Laboratory on the east and the west coasts, Oak Ridge National Lab, and on the west coast, 2 of the 3 California labs, the Berkeley Lab and the Lawrence Livermore National Lab. Okay, so as you know, the oil and gas sector has diverse needs for sensing and measurement tools. In this slide, we begin upstream. So sensing technology offers the potential to provide important downhole and surface measurements that can help to optimize operations, ensure safety, and reduce environmental impacts. Now we'll look at the midstream, where we're looking at compressors, transmission, pipelines, and so on. And one of the main issues here is leaks in the pipelines and failures. So there are technologies that exist for leak detection, but the current monitoring tools are highly limited when it comes to identifying sources of failures before they occur. Enhanced midstream sensing capabilities would help mitigate the significant economic, safety, and environmental impacts of a pipeline incident. Some of you are familiar with the fact that currently measurements are made on the pipe. We're talking about putting large lengths, maybe 100 kilometers of spliced together fiber within the pipe to pick up measurements. Okay, so the Department of Energy's vision for an integrated laboratory R&D initiative is focused on developing intelligent oil and gas infrastructure through technologies that allow for early warning of impending failures before they occur. And this includes sensor technology, field validation, sensor deployment applications, physics-informed analytics approaches, including machine learning and big data management. So you see this sort of very large Venn diagram with overlaps. Sensor technology is only one piece of the puzzle. Physics-based data analytics can help to guide the highest value sensor technology development to address gaps in existing information. Many of the oil company research labs that I've worked at, the service companies, the government, academia, use what are known as technology readiness levels. Very early technology is TRL1. Getting towards commercialization are levels like 6 and 7 and so on. And there are fiber optic DTS, DAS measurements that are being made in the field. So a variety of sensor technologies are under development. Work at labs range from early research TRL1 all the way to full-scale field development. deployment, data management, analytics 6 and 7. Fiber optic technologies include commercial ones such as DTS, DSS, DAS, early stage research including distributed chemical sensing or DCS, and preliminary ideas such as how quantum sensing can be integrated with optical fiber sensing platforms to make an impact in the industry. All right. When I got to the Department of Energy, there were 4 separate labs that were working on fiber optic and sensing applications, and I worked with them to all work together, and I basically put this slide together using materials that they gave me. On the left is NETL, National Energy Technology Laboratory at the top. On the right top is Berkeley Lab. On the bottom left is Oak Ridge, and on the bottom right is Lawrence Livermore. So this graphic shows ongoing activity and capabilities in fiber optic sensing technology research across 4 of the labs that I just named. Together, the lab capabilities and ongoing efforts range from TRLs 1 to 6+ and represent the full spectrum of research and development for advanced distributed optical fiber sensor technology. So on the top left, we have NETL. It's focusing on enabling distributed chemical sensing, new distributed interrogator technology development. So that's the source of the light that propagates through the fiber and gets scattered or transmitted. High temperature single crystal fiber growth for extreme environment applications, including geothermal. NETL has ongoing work in national gas infrastructure, carbon sequestration, which is, among other things, monitoring carbon dioxide plume migration underground, and ultra-high temperature applications for power generation techniques such as solid oxide fuel cells and other applications, which gets us into the clean coal space. On the bottom underneath, Oak Ridge National Lab has unique expertise in quantum sensing through long-term investments by the Office of Science, and has applied this expertise to photonic sensors and is starting to get into optical fibers. At the top right, Lawrence Berkeley National Lab is the DOE leader in the applications and field deployment of existing distributed optical fiber sensing technologies, including distributed temperature sensing, distributed strain sensing, and distributed acoustic sensing, with a particular emphasis on carbon storage and other subsurface applications. And on the bottom, and we'll go through this and the others in more detail, this is Lawrence Livermore. So it's trying to apply physics-inspired models to better understand how DTS, DSS, and DAS can provide operator-relevant information through simulated data sets and neural network algorithms. It also has a draw tower that I've personally visited, which enables one to design custom fiber to enhance the performance of the distributed optical fiber sensing modalities. Okay, so this is a little bit more on Berkeley Lab. There's a lot of stuff in this slide. I'll give you an overview. Berkeley Lab has broad experience with distributed fiber optic sensing deployments. The lab's expertise includes novel deployment strategies that can reduce costs and enhance the value of various types of data sets for operators. And it's pushing towards higher resolution in time and space using semi-permanent sources and distributed sensing. These are 3 examples of unique measurement systems beyond DAS deployed and developed by Lawrence Berkeley National Lab. We'll start from the left and go over to the right. So this is continuous active source seismic monitoring, or CASM Chasm. So it's an approach they've been working on for the last 10 years or so, based on using semi-permanently installed borehole source and receiver arrays for high-speed subsurface imaging. The components are arrays of piezoelectric sources coupled to a fast high-voltage switch to allow acquisition of tomographic data sets in as fast as 30 seconds and soon even faster. This allows imaging of fast processes, including carbon dioxide movement and fracture emplacement, with excellent signal repeatability. CASM received an R&D 100 award in 2015 and will be the prime tool for geophysical monitoring of stimulation, refracturing, and enhanced oil recovery in the recently DOE-funded Shale Field Lab in the Eagle Ford. An outgrowth of the CASM work has been more recent development of automated permanent surface seismic sources based on orbital vibrator technologies. That's the one in the middle. So surface orbital vibrator SOV systems are useful for long-term reservoir monitoring with broader aerial coverage than borehole methods. The source is GPS synchronized and can be used in concert with DAS for monitoring both deep and shallow subsurface processes. The system is currently being deployed at several deep GCS sites, Otway and ADM, and has been, so that's carbon storage, and has been tested for near-surface monitoring applications, including a permafrost project in Fairbanks, Alaska. On the right is SIM-FIP. So a recently developed SIM-FIP tool uses a straddle packer and a precise fiber-optic tensor strain measurement system to measure the properties of fractures or faults as stress is perturbed. The tool has now been used in fault manipulation experiments to better understand the impact of pore pressure on slip. Distributed acoustic sensing, or DAS, is based on laser light scattered by inherent heterogeneities within the optical fibers, and improving the technology from both a hardware perspective as well as a data interpretation perspective are things that are being worked on. And people in the field say that this offers immense possibilities for subsurface characterization and monitoring. Custom distributed acoustic interrogator instrumentation has been developed, and new fiber designs, including inline processing for fabrications of weak gratings, are being pursued in recently established program efforts by both the Lawrence Livermore Lab and Lawrence Berkeley Lab. Lawrence Livermore Lab's draw tower facilities are being leveraged, and the goal is to enhance the performance of distributed acoustic sensing by developing novel fibers with enhanced performance. These are fibers that are not yet commercial. Now we'll move to Lawrence Livermore. Geomechanical models are being developed to enable and improve quantitative understanding of distributed acoustic sensing. This allows for training of advanced data analytic methods without being constrained simply by information that can be gathered from a particular case study of a single field deployment and study. This example shows how the developed models can be used to simulate specific processes within the subsurface environment and then to generate synthetic DAS data for various assumed configurations of distributed optical fibers within the subsurface. So this is also going to help you to determine where you should put the fibers in wells in order to make valuable measurements. But we see that we have a synthetic data set and we can measure attributes on that data set. Okay. So the corresponding synthetic DAS data sets from a large number of simulations, so there's a catalog on the left, can be integrated into neural network algorithms in order to train the neural network to allow one to extract output features that are relevant to an operator from the input DAS signal. So in the example shown here, we have a synthetic catalog. We can supplement it and calibrate it to actual field measurements of DAS. We show you one of the input signals. We take certain attributes that we measure on the input signal. We put this through a deep neural network with a number of different layers, and we relate it to output features. So fracture height, fracture length, and then the distribution of proppant within the subsurface. The people are starting to do more and more work here. This allows us to integrate the reservoir modeling, the DAS measurements, and the machine learning into a coherent workflow. Now, in addition to applying and improving existing distributed fiber technologies such as strain, temperature, and acoustics, NETL Lab is pursuing the development of enabling technologies for distributed fiber optic chemical-based sensing. Applications of distributed optical fiber sensing include wellbores and pipelines, in which chemical-based sensing modalities enable detection of early corrosion onset or other parameters indicative of failures and incidents before they occur. This allows the operator to take preventive actions that mitigate costly failures in terms of economic, safety, and environmental impacts. Direct methane leak detection for natural gas pipelines also enables more direct measurements of leaks and potential information of smaller leaks than possible through indirect measurements. DCS, that's the distributed chemical sensing, it is an earlier stage compared to the more traditional modalities of DTS, DAS, DSS, and requires significant ongoing research and development in the coming years to facilitate technology maturation and deployment. Distributed optical fiber-based chemical sensing requires significant technological advances relative to physical parameters, such as temperature, strain, and acoustic. One primary approach is through integration of functional materials that have specific interaction with analytes of interest, such as methane, carbon dioxide, hydrogen sulfide, pH, corrosion, and so on. Many types of materials are being developed and integrated with the fiber optic sensing platform. Novel distributed interrogation approaches are required to allow measurements of spatially resolved chemical information. To explore opportunities for the most significant impacts of distributed fiber optic-based sensing, a detailed survey of techniques for distributed interrogation is being pursued. The goal is to understand how different methodologies can be applied across oil and gas applications and to determine opportunities for improvements through advanced scientific and engineering principles. Developing new interrogation techniques for distributed chemical sensing is also a major effort and goal of this initiative. In addition to new interrogation methods, integration of fibers along a pipeline coupled with advanced analytic methods such as AI and machine learning offer the opportunity for identifying leaks or other incidents based on distributed acoustic sensing signatures. NETL is collaborating with the University of Pittsburgh in pursuing this concept, which complements the ongoing work in corrosion offset and direct methane leak detection in the laboratory under the National Gas Infrastructure Program. Okay. When I was at the Department of Energy, the department was funding efforts in so-called exascale computing, and having come from the world of quantum mechanics, I was a theoretical physicist in graduate school and then became a geoscientist and petroleum engineer. I asked, what about quantum computing? So they put me in touch with Lawrence, Livermore, Berkeley, NETL, and especially Oak Ridge. And so I asked, when are quantum computers going to be ready to do large-scale, multi-scale, multi-chemistry, multi-physics reservoir modeling? And they said, we're doing very simple systems right now. So that would be maybe 10 years away. And this conversation was 2018. They said, but quantum sensing, or hybrids of quantum sensing and classical sensing are already being worked on and should be available within a few years. So they gave me these slides. I'm by no means an expert, but I'll go through them to tell you a little bit about the world of quantum sensing. So quantum sensing is the use of quantum effects to enhance some aspect of a sensor, typically with the goal of enhancing the signal-to-noise ratio or to detect very weak signals that were previously undetectable. So as an example, atomic clocks used in GPS location are one example of a quantum sensor in use right now. Quantum sensors are typically used to detect things that are femtometers or smaller in size. The quantum sensors can be huge. There's something called LIGO, the Laser Interferometer Gravitational Wave Observatory, which does quantum sensing, and that's many kilometers long. One of the things that we're trying to do here is to reduce the noise limit. So we can reduce the noise of a sensor down below the current minimum noise allowed in classical systems, which is called the classical limit. And beyond that, to get down lower, quantum mechanics is needed to go further. The goal is to push the noise floor down and the dynamic range up using quantum effects. And we achieve this using two major concepts: quantum noise reduction and quantum entanglement. So we'll take a quantum noise reduction first. This shows vaguely how quantum noise reduction works in a nutshell. For a sensor with an optical readout, for example, the absolute lowest noise the sensor can achieve is given by the variance of the optical readout field. If all other sources have been made much smaller, it's completely possible to get this level in many sensors, including off-the-shelf sensors, and is an area in which National Energy Technology Lab has expertise. Once you reach this point, the noise denoted by I of t on the slide is determined by the Heisenberg uncertainty principle, which, if you still remember basic physics, talks about trying to make measurements of complementary variables like angular momentum and angle, or energy and time, and so on. It's possible to reduce the noise in a particular variable you're interested in. In this example, the variable would be optical intensity, at the expense of some other variable you don't care about. In the shown example, the excess noise is in the phase of the optical signal, but we're not measuring the phase, and therefore its noise doesn't affect our signal. The noise reduction is achieved with special nonlinear optical media that enable optical fields at different frequencies to interact with each other. In typical media such as optical fibers, fields at different frequencies normally don't interact. Therefore, the goal is to transduce the signal we care about onto a readout variable that has a quantum noise reduction on it, and the signal to noise reduction boost is equal to the amount of quantum noise reduction. The other way to improve this is with entanglement. Entanglement is a superposition between at least two quantum states. The measurement of any one subsystem collapse is a superposition, so you know what the measurement result in the other subsystem would be, but you still have to check to be sure. Doing a measurement on both subsystems at the same time results in reduced uncertainty, which implements quantum noise reduction across more than one system. Many classical sensors use a reference beam that is split off from the signal beam as a noise reference to remove any excess noise from the signal, but the method only lets you get to shot generated noise, which is dictated by the Heisenberg uncertainty principle. Using entanglement to create multi-parity quantum noise reduction, you can replace the classical signal and reference beams with entangled beams and get a signal to noise reduction improvement in difference measurement that goes beyond the shot noise. You can reveal signals that were previously hidden in the noise, as in the slide plot, which shows a lower noise floor due to entanglement after the joint measurement. So this is some pretty heavy duty stuff. What you want to know is that we're trying to improve the signal noise. The quantum noise limit can be 10 dB or maybe even more than the classical noise limit. We're trying to improve the dynamic range. One of the applications that I was interested in is many oil companies, so let's talk about oil and gas for a moment. We can also talk about CO2. Try to monitor fracture propagation, but also where the proppant is going. And there are some high-tech boutique companies that are developing nanosensor transmitters that go into the proppant. And then we use various measurement techniques using fiber, classical fiber, to try to monitor where the proppant is going. But in some cases, the signals from the nanotransmitters are very weak relative to the classical noise limit, and we think and we hope that if we go to a quantum system, or at least a hybrid classical quantum system, we can get a better handle and possibly read these nano signals in the presence of noise. And if we do quantum, it would be quantum noise, so we have a better signal to noise ratio, and that's what we're trying to achieve. I'm going to skip this one in the interest of time, but I'll tell you that to date, Oak Ridge has applied quantum enhanced techniques to photonic sensors, but it's just starting to explore coupling with optical fiber platforms to generate distributed optical fiber-based interrogation methods. Now let's talk a little bit about machine learning. On the left describes what capabilities we have at the DOE and the national labs, and on the right where the operators come in. So applying machine learning to subsurface and operational data from oil and gas operations offers many benefits to the Department of Energy as well as to operators in having multiple national labs apply machine learning techniques to their data. There are also many companies in industry now that are working on machine learning, and many oil companies are going out to hire data scientists. And so we have a challenge, which we show on the right slide, right hand of the slide. We need both subject matter experts, engineers and geoscientists, as well as data scientists. The subject matter experts understand the data, they understand the business priorities and how to validate the data. They also understand physics-based models if they're doing, let's say, reservoir simulation or geomechanical modeling, and laboratory measurements. The data scientists understand the different tools and approaches. And so we really need a good overlap between those two skill groups. This is a little bit of an older slide. It says industry has primarily the subject matter experts. The national labs have both the subject matter experts and the data scientists. And the labs can engage academia and other research organizations. So it's that overlap that's really important. Okay. You know, there's many ways of doing data analytics. Some of it is purely data-driven. Some of it is model-based. People call the model-based a physics-based. It's really science-based. Some of it has chemistry. Some of it has biology. There's some simple ways to do this that I described in an earlier talk this week. So go back and play P.A.S.S. number 2. If you didn't hear that one, it was on technology integration. And we explain a little bit there about using full physics, but simplifying the procedure using what's known as ROM, reduced order modeling. So as a summary for what we're trying to do, for the unconventional reservoir, some of the objectives of the operators are shown on the right. We want to optimize resource recovery. We want to reduce the numbers of poor and failed wells. We want to reduce the interference between wells, parent-child interactions. Do you know that in many of the plays, the shale plays, something like only 25% of the stages are contributing to 75% of the production? So if you have a way through modeling and data and engineering of being able to predict how many stages you need and where to put them along a horizontal and what the length of the horizontal should be, you could save a lot of money. Your cost benefit would be very high. Your benefit to cost would be very high, and the project profitability would go up. The second bullet on the right, more and more people are starting to look at autonomous systems. Right now we have a human in the loop. We send out an engineer to the field to do preventive maintenance. How about sending an engineer out only when you get an early warning that there might be an incipient failure, and that's when the engineer goes out? Not at all times. And so we avoid a lot of waste, and we also reduce the exposure of the engineer to field accidents. So we're looking for autonomous systems with early warning to reduce the use of water, reuse of water and use of water, and to reduce the time to optimize new plays. So a summary of this whole thing is a process is needed to effectively incorporate machine learning to significantly increase production from unconventional shale plays while improving safety and decreasing environmental impact. Because data sets from the field for these shale plays are often not complete or comprehensive enough for the big data analytics that are available, it's useful to complement them with data from laboratory studies and high fidelity model results. So approaches need to be developed to manage all of the different types of data streams and to apply a variety of analytical approaches to achieve the desired outcomes. This is an example study. This is the Marcellus shale gas in Pennsylvania. And what we're trying to do here is to look at the first 12 months of cumulative production. We're going to look at some good performing wells, well-performing wells, and some poorly performing wells. They will have different engineering variables like perforation length, chemical additives, and so on. They will also have different reservoir variables shown in red: the frac type, the pyrite fraction, the total organic carbon, the natural fracture density. We want to learn from field measurements, and we definitely need that for the engineering variables, and then from field measurements and models and lab measurements. So we're going to need that for the reservoir variables and the heterogeneity, so that we can try to describe the initial production in terms of a small number of very important variables that the production is sensitive to, and then we can look elsewhere in the Marcellus where we haven't placed a well to find out which engineering practices are the best and what types of reservoir we should be putting our wells in so that we can improve our production. So machine learning and data analytic approaches are being used to help identify which properties are important, pardon me, for predicting well productivity and to help operators tailor wells to improve recovery. As shown in the middle, there are several different algorithms that were tested. And in this particular study, the Kernel Ridge method proved to be the most successful for the publicly available data included. Public data is all in black, and then the proprietary data is shown in red, the TOC going down a micro-family. Work initiated in the Western Marcellus Shale will be extended to other parts of the Marcellus and then to other plays. The fraction of pyrite, the TOC, the natural fracture density, and brittleness are being considered as specific additional geological parameters to use in the machine learning. Algorithms based on some of the fundamental shale studies, as well as additional operational parameters that were unavailable for prior studies, such as the rate of proppant injection and details about the completion engineering type. Novel sensors, such as those highlighted today, could add new dimensions to this type of analysis and potentially enable significant improvements to reservoir performance. Okay, so here's a summary of key messages. The DOE lab system is aggressively pursuing an integrated distributed fiber optic sensor R&D program. Pardon me. Ongoing efforts at 4 labs range from basic fundamental research studies to full-scale field validation and deployment. Coupling advanced sensing techniques with physics-based machine learning and AI enhances the value of sensing and measurement data to address critical information gaps. With that in mind, development of an intelligent subsurface engineering initiative is underway to leverage novel sensor technology. Pardon me. I want to thank Dr. Paula Hodnicki, who is formerly at NETL and is now an associate professor at the University of Pittsburgh, who helped me put together today's talk. And I want to thank you for your time. You can follow us on LinkedIn to receive updates of the P.A.S.S program. I'll now try to address any of the questions or issues you may have, or to forward them afterwards to experts in some of the sub-disciplines that I described today. Thank you very much for your attention.
Yeah, thank you very much, Alan. Can you hear me?
Yes.
Yeah, it was very an excellent presentation and a very informative one with respect to the state of the art in fiber optic. I would like to invite attendees to send their question actually in the chat section. Since we are receiving the question, Alan, I have an overall question to you. How do you see the future of fiber optic in subsurface engineering, specifically oil and gas or geothermal? Do you think that the current sensing and measurement technology will be totally replaced by fiber optic based methodologies, or it will just take part of the market?
There have been a number of studies that have been made by companies. I don't want to mention names, but I have friends at a number of fiber optic companies where they have done borehole sensing applications using either three-component geophone arrays or with optical fiber. And with the optical fiber, you're measuring either a compressional wave or a converted wave. But people are also working on helical fiber so that you can measure three components. And the fidelity of the measurements, the ease of the measurements, the ruggedness of the fiber, and so on. Eventually, these geophone arrays, given a few years, I believe are going to be completely replaced. With the fiber, we talked about unconventional applications here today, but there's lots of conventional applications, especially if you're drilling through salt or trying to image the salt faces and the base of salt. The BP and other companies are working on. I believe that we're going to be fully instrumented. We're going to be not only talking about the internet, but the Internet of Things. You can also use optical fiber, maybe buried in trenches at the Earth's surface, but to replace a lot of surface geophone spreads as well. So lots of future for this.
Thank you, Alan. A very interesting question by Samin. Could we apply DAS for static, semi-static rock deformation around wellbores due to hydraulic fracturing or CO2 injection, or should we use DSS?
Or should we go ahead?
And should we use DSS? I don't know what it stands for. Samin, can you clarify on that?
It's strain sensing.
Oh, okay.
Yeah. I think DSS may be the way to go. If you're sensing microseismic waves and things like that, there's a frequency dependence to that. It may be adiabatic. The engineering measurements are isothermal, bigger strain, and so on. I think DSS may be the way to go for things like borehole stability. I will refer you to any of a number of commercial. This is commercial technology. This is not research, and that's good, but you can engage with a number of, I'll give you names of companies offline, but not on this broadcast right here, of my friends and others at fiber optic companies, and I think DSS would be the way to go for that.
Yeah. Rick is asking to comment a bit more on how DCS works. From info on the slides, he got the impression that it relies on coatings on fibers, but he's interested to get a little more insight about the DCS.
Yeah, it does certainly look. I'm back at one. It's labeled slide 17, but the numbers on the slides do not necessarily correspond to the order here. But yeah, it looks like these are either films, metallic films to look at corrosion, or coatings. The person who put this slide together and the world expert in this is Dr. Paula Hodnicki of the University of Pittsburgh. And so if that individual will just send me an email, I will hook you up with Paul, and he'd be glad to talk to you in great detail about what he's working on and how this works. There's some rather primitive techniques, for example, in pipelines, and you can think of boreholes where you're looking at corrosion, eventually cracking, and then you get leaks or worse in a borehole. And to be able to have the ability by looking at chemical changes, that will tell you that the pipeline will start to develop axial cracks and so on is really the way to go. And so this is terribly important. It looks like pH is also one of the things that is being monitored here. I've now given you my elevator speech, which is maybe 13 words more than what I said when I showed this one. So I will hook you up with Paul. When I made these slides available publicly, there was a lot of interest in the chemical sensing. And what I prefer to do, because I'm not an expert in that area, is to just hook you up with Paul on that. But we'll tell you more. As soon as Paul tells us, we'll tell you.
Thanks, Alan. Mojtaba is asking about the common use of fiber optics in CO2 sequestration project. Is it only for monitoring or there are other applications to it?
Yeah, there was an application here. I think they're doing a lot of testing and so on. If we go back to this one that's up right now, and I'm looking at the right at Berkeley Lab, this was a demonstration project, but it's 7 years old, and it's for CO2 sequestration. So I think they're monitoring where the carbon dioxide plumes are going, and they're also monitoring whether there's any fracturing or degradation of the reservoir over time. This next one has one which is Otway, and this is monitoring CO2 storage. So they've got some cross-well type thing here with an injection well and a monitoring well, and they're looking at a number of different levels. They have microseismic sensors, and then they also are measuring pressure and temperature and so on, and looking at the gas cap. So we can get you more work, more information about this as well.
Okay, Gonzalo is asking about any progress on the H2 degradation on downhole fiber.
I don't know the answer to that question. I will try to find that out. I do not know the answer to that.
No worries, Alan. The next question is from Fushan. How is the shear motion considered by the traditional fiber optic sensing technology?
Yes, so this fiber is measuring compressional waves, and it's measuring converted waves. So a wave goes down as a compressional wave and hits an interface somewhere in the earth, and then that converts to a shear wave coming in at some sort of an angle, and then that's being measured. So that's essentially what you're getting, as opposed to measuring pure shear. But there are companies, again, I don't want to mention names, that are in the business. Some of them are working with the Department of Energy for small business loans that are developing helical fiber optic cable that will be able to make 3-component measurements. So you'll get vertically polarized shear waves as well as horizontally polarized shear waves.
Another question from Mojtaba, is there any recommended DTS resolution for CO2 injection projects?
Don't know the answer to that one either, except to say that, you know, the fiber optic companies, first of all, if you look at this slide and go to the last bullet, it says experience in oil and gas, carbon storage, geothermal, and environmental. The national labs and industry started working almost entirely in oil and gas, and then the national labs have been working for about the last 5 years very heavily in carbon storage. So I'll get some references for you. The industry is just really catching up. If you want to go to a commercial provider for carbon storage or geothermal, they've been working in these areas for the last couple of years, and offline, but not during this talk. I'll give you the names of some of them, and you can go to their websites, and you'll see lots of displays. You may even see some dimensions to answer your question for oil and gas, for carbon storage, for geothermal, and groundwater and other environmental. So,
yeah, and we got the last question from Islam. He's thanking you for your presentation and asking if fiber optics can help identify the critically stressed faults which have already slipped. What about its application in franchite and parent? Sorry, I think it's the frag child and parent well interaction.
Yeah, well, people these days, you know, are using microseismic and other measurements to look at that. And a lot of the microseismic measurements are being measured in arrays, either near the Earth's surface, on the surface, or in the borehole. And just about anything that you can do with those arrays, you can do with the fiber. So you ought to be able to look at signals in order to help with that. I will tell you that the other thing to do is, as we had in some of our slides, so I'm going to, you know, I would think this sort of thing, you put fiber and you make measurements, but you also make models. And you could make a synthetic catalog where you assume certain spacings between horizontal wells, between parent-child. You could then change the spacing. You could put the fiber in boreholes, and you could put it at various depths. And by doing that, you can see how far apart you have to put the horizontals before you start to have frac hits, parent-child interactions. And you could also see where you have to put the fiber in the boreholes at what depth and how far away in order to be able to monitor the parent-child interactions. So I think it's this type of approach, combining modeling, measurements, different trial parameters, and using machine learning in order to see how you can improve and mitigate and maybe even remove the frac hit problem. So I thank everybody for their attention. If you have additional questions, you can send them to me at this one, and then I can bring in experts. The national labs would like to develop relationships with people from industry. We at Petrolern already have very good contacts at the national labs, so we're a little bit ahead. So you can talk to us, but you can talk directly with the national labs. They would love to talk with you about the work that they're doing, to understand their issues, and for you to get full benefit if you are a U.S. resident of your American tax dollars. So with that, thank you so much. And the next talk will be P.A.S.S. 5, which is on Friday.
Yeah, thank you very much, Alan, for your patience answer the question. I'm sure you deserve a glass of wine now. Thank you everyone for attending the meeting. Don't forget Friday is our next talk by Hasbel Yadi, and he's talking about machine learning and its application in production optimization. So have a great day or night wherever you are, and we meet you again on Friday. Thank you.